I am absolutely fascinated by this high-stakes topic, and today we're diving headfirst into the extreme physics and incredibly complex engineering behind hypersonic missiles. If you've been seeing headlines about these weapons and wondering how on earth they actually work, well, you are definitely in the right place. We're going to break down the mechanics, the mind-bending thermodynamics, and the very real global defense implications. Let's get into it.
So, here's our roadmap for today. We'll kick things off by defining what hypersonic flight actually means. Then, we'll look at the brilliant engineering behind scramjets before exploring China's DF-17 glide vehicle, Russia's Kinzhal missile, and finally, wrapping up with America's ARRW program.
All right, Section 1, Defining Hypersonic Flight. To truly understand these weapons, we first need to strip away all that dense military jargon, because as you'll see, making something hypersonic isn't simply a matter of strapping a bigger engine onto a rocket.
The absolute crucial point here is that a hypersonic missile isn't just about going fast. It requires three mandatory attributes to fit the definition: extreme speed, mid-flight maneuverability, and pinpoint accuracy. You see, while traditional ballistic missiles go incredibly fast, they follow a highly predictable arc. A true hypersonic weapon, on the other hand, dynamically maneuvers mid-flight to hit a very specific target.
To really grasp the immense scale of these speeds, we use the speed of sound, or Mach 1, as our baseline. Those commercial airliners we fly on, they sit safely in the subsonic category. Modern fighter jets push into the supersonic realm at around Mach 2 or 3. But to actually be classified as hypersonic, a vehicle has to reach Mach 5 and above. And the real-world implications of those numbers are just staggering. Sure, a space shuttle can briefly hit Mach 20 or 24 during re-entry, but hypersonic missiles sustain these speeds over vast horizontal distances. We're talking about crossing the Mach 25 threshold. That is literally around 19,000 miles per hour. To put that into perspective, that turns a massive distance like the US to China or New York to Russia into a remarkably short flight time of just 18 minutes. Moving right along to Section 2, the engineering behind scramjets. Let's look under the hood and see how engineers actually solved the massive physics problem of extreme heat and friction at those speeds. When we break down the anatomy of an air-breathing hypersonic missile, we see a highly organized, totally wild piece of engineering. Notice that solid booster at the bottom. That's often a modified ATACMS supersonic missile. And it is critical because a hypersonic engine doesn't just work from a standstill. It actually relies on that booster to reach the necessary altitude and hit Mach 1 before the main engine, the scramjet, even wakes up. Above that, you've got your hydrogen tank, the avionics, and the front cone carrying the warhead.
Now, to really understand the scramjet, let's contrast it with a standard ramjet. A ramjet takes high-pressure incoming air and actually slows it down to subsonic speeds before igniting the fuel. The scramjet, however, has a completely different challenge. It maintains supersonic airflow through the entire engine. Think about trying to keep a match lit in a Category 5 hurricane. That is essentially what a scramjet is doing, maintaining stable combustion in an airflow exceeding 19,000 miles per hour.
Let's walk through this brilliant thermodynamic solution step by step. Look at the second step specifically. At these insane speeds, friction causes intense, destructive heat. So engineers solve this by using the hydrogen propellant to literally cool the incredibly hot engine walls before it's ever even injected for combustion. It's a dual-function system that keeps the missile from melting in the atmosphere before it expels energized gases to push itself way past Mach 5. All right, Section 3, China's DF-17 Glide Vehicle. Having established the mechanics, we're now going to look objectively at our first real-world application, diving into the specific systems deployed today. $120 million. That staggering number represents the cost of just a single solid-fuel DF-17 weapon. It is a massive piece of hardware, weighing in at roughly 15,000 kilograms and measuring about 11 meters in length. Source data indicates this massive glide vehicle has an operational range of around 2,500 kilometers. And while it is fully capable of carrying both conventional and nuclear warheads, it's engineered specifically to threaten large, moving targets like U.S. aircraft carriers, which presents a very specific tactical challenge. Pay close attention to this launch sequence because it's fascinating. It begins on land with a heavy-duty truck, but the real danger happens at steps 3 and 4. After the initial high-altitude ballistic launch, the actual glide vehicle separates and drops to a very low altitude.
By skimming the land or sea and simultaneously changing its trajectory mid-air at Mach 5, the DF-17 becomes incredibly difficult for carrier strike groups to detect on traditional radar, let alone intercept.
Next up, Section 4, Russia's Kinzhal missile. Transitioning from China's ground launch system, let's objectively examine the airborne mechanics of Russia's tried and tested Kinzhal. This visual breakdown shows a massive weapon that analysts note is structurally very similar to Russia's land-based Iskander ballistic missiles, but ingeniously adapted for the sky. You can clearly see the distinct sections, the steerable fins in the midsection for maneuverability, the core rocket motor, and a massive 500-kilogram nuclear-capable warhead sitting right at the tip. All of that engineering propels the Kinzhal to an astonishing terminal speed of Mach 12. That equates to roughly 14,700 kilometers per hour, carrying that massive payload over a reported range of 2,000 kilometers.
Notice how this air-launch system essentially uses a supersonic jet as its very first stage. Because the missile itself is extremely heavy, a MiG-31 Foxhound interceptor carries it, already traveling at Mach 1.4. Once the pilot releases the weapon, a protective cap safely ejects, and then the missile's own engines ignite. This gives the Kinzhal a massive, already supersonic head start before it even begins its own burn.
And finally, Section 5, America's ARRW program. Let's explore the United States' primary hypersonic initiative, the AGM Air-Launched Rapid Response Weapon, better known as the ARRW program.
The financial scale here is just massive. It's a Lockheed Martin system funding a two-part weapon that contains both a booster rocket and a highly advanced glide vehicle housed safely beneath a protective cover. At $18 million per missile and a total program cost of $2.2 billion, it represents a major focus of U.S. defense research. So here is the operational sequence. The ARRW relies on the iconic B-52 bomber as its transport, dropping the weapon right from under its wing. The booster engine fires to cover the first few hundred miles. But what is truly mind-blowing about this sequence is Step 4. After the covers pop off, the glide vehicle hits its target completely unpowered. It uses absolutely no explosives. It relies entirely on the sheer kinetic energy of traveling at Mach 20 to create an impact just as powerful as a traditional bomb.
The intent of this system is to target adversaries' aircraft carriers by dynamically skimming surfaces and evading traditional anti-air defenses. However, looking at the current status, impartial reports currently categorize this multi-billion-dollar program as struggling. Some reports even use the word failure, though unofficial testing and experimentation are very much still ongoing.
Which brings us to a really provocative question to wrap up this explainer. We've seen the incredible aerodynamics, the staggering costs, and the sheer capability of these glide vehicles to travel up to 19,000 miles per hour while changing trajectory on a dime. The immense challenge these feats of engineering pose to the future of global defense is unprecedented. I mean, think about it. How do you hit a bullet with another bullet when the first bullet can literally dodge out of the way? Thank you so much for exploring this highly complex topic with me today, and keep learning.